Hello YouTube, this video is going to serve as an introductory video to sequences and what we mean when we talk about sequences in math, okay? So we say in math the word sequence is used in very much the same way that we use it in ordinary English. That is, we say anything that's a collection that's listed in sequence means that it's ordered, okay? So that it has like a first member, a second member, a third member, and so on, okay? So we say, mathematically speaking, we could think of sequences as a function whose domain or input values is a set of positive integers. So what we could do is we could actually just like consider maybe what a sequence would look like here. But maybe let's say we have some particles here, some, I don't know, like some configuration. What we're saying here is that during the first moment that there's one particle here. So I can say there's one thing in the first spot. So we say this is our first term in the sequence. But what happens is in the next moment, now we have like this configuration here, maybe like a triangular configuration. Now I have, in the second spot, it looks like we have 4 elements. And then we say, if I were to add to this here, we say 1, 2, 3, 4, 5. We say total how many do we have? Well, we have the original 4 plus 5 more. This is 9. Okay, so this is like my third element. And if I were to keep doing this, what we see is some pattern that occurs here. But we say maybe the fourth element, I would have to add 1, 2, 3, 4, 5, 6, 7, 8. We say 8 more. But basically, we could say the fourth spot, if I were to add 1, 2, 3, 4, 5, 6, 7. Sorry, 7 to this, we get 16. So basically, what you could see is that this sequence of events like here could continue to go on like forever and ever and ever and ever and ever. And if I were to keep adding these on, I would have like the 5th and 6th and 7th iteration. But we'd say in general, what we tend to do is we tend to refer to as the nth term of some sequence. Like if I were to go out, like however many steps past the first step, what would be in this output spot right here, okay? What I can tell you is it'd be easy to figure out. Actually, I don't know if anybody's recognized that these are just the squares of these bottom numbers right here, okay? So I want to point a few things out here, starting with this. First things first, a sequence can be thought of as like a function. It's just that when we think of things as functions, we typically think of them as like x and y. In this case, we're going to be using n and then like what we're going to call not like f of n, which we would normally say is like some y value. But in sequence notation, what we're going to use is what we call subscript notation. So for instance, up here we say, okay, well, we say sequences are functions, but the domain is, the set of positive integers. The things that we start with are a set of positive integers because we say n represents the term, okay, that we're at in the sequence. So like my first term or my second term or my third term or my fourth term, we'd say that, up here we were getting 1, 4, 9, and 16. We can see that there's this functional relationship here, but we'd say looking at the domain, we say domain starts at 1. Okay, so essentially, that's what we want to point out here. Sequences are just functions whose domains start at 1, and they only plug in whole numbers because we're talking about a term in a sequence, like the first term, second term, third term, fourth term, and so on. So that being said, I say notice rather than using function notation, so instead of f of x, we're writing our terms of the sequence in what we call subscript notation. So we use n to indicate the term that we're at, but we use a sub n, kind of like an f of n notation. And you'll see both of these, but get used to this, and we call this the output, okay, of our range value here, or a y value, you could look at it here, of our sequence here, but a sub n. So a quick commentary on this one. We say for any sequence in general, we say given the first term, we say the second term, the third term, and so on and so forth. We say that we get a1, a2, a3, and if we had like the nth term here, we say nth term, we would call this an. But the idea is this. We use a with a subscript to represent that it is the term in the sequence that is that term right there. So we say like a sub whatever is saying that it is the nth output of this sequence, okay? So if all these are just functions, that's all they are. And we say we have some term, and it goes to some output over here. We say it goes to some a sub n, and it has a rule, okay, basically. And we say that this rule basically tells me how to get from the term over to the output here. Then what we want to do is we want to define these kind of like a function and treat them the same way. So we say an infinite sequence, kind of like this one over here, this triangular one. If it were to go on forever and ever, we could see how we have some sequence of things where there's a first, second, and third thing, but it goes on forever and ever. We say an infinite sequence is a function whose domain is the set of positive integers. So that is, our term numbers start at 1 and then go on forever and ever. It says the function values are these. So we say a1 is our first term, A2 is our second term, A3 and A4, and AN, these are our nth terms in general, of this sequence that goes on forever and ever, but we call these the terms of the sequence. We say if the domain of the function consists of the first n positive integers only, then the sequence is considered to be a finite sequence. That is, in other words, if we say n, we say the sequence only goes from a1 out to a, say n is 10. We say out to a10, then 10 terms of a sequence would only be what we call a finite sequence, okay? And last but not least, I say sometimes it's a convenience to start a sequence with a subscript of 0 instead of a 1. So that is, sometimes we have what we refer to as like a 0th term in the sequence, okay? So anyways, we're going to go ahead and look at just really quickly here how you would write out some terms of a sequence given the rule. But we say write the first 5 terms of the sequences given by the following rules for finding the nth term. So now the thing that's really important here I want to point out is this. In this first case, we say a sub n is equal to 3n minus 2. Okay? In other words, we would be treating this in any other problem this way. We would have been treating it this way like a function, but we're saying that a function has a domain of all real numbers, whereas a sequence only has, say, a first term and onward. So what I'm going to do for this example is I'm going to fill in a table. We say a sub n and n, okay? So we say starting at 1, 2, 3, 4, and 5. We wanted the first 5 terms of the sequence. All we're really doing is substituting these into the problem here. So when it says n is 1, what we're really looking for is a1. But what I want you to see is that when n is 1, then we also need to put that into our rule. So we say really we get 3 times 1 minus 2. So a sub 1 is really 3 minus 2, and a sub 1 is 1. So our output is 1. And then we did this just like plugging it into a function. So again, if we were to plug in 2, we say what is our second term in our sequence? a2. And this would be 3 times 2 minus 2. So 6 minus 2 would be 4. In this case, I would notice if I plugged in 3, I'd get 3 times 3 minus 2, which is 9 minus 2, which is 7. I noticed that in this particular case, that these keep going up by 3 every time. Okay, so this sequence, which certainly could go on forever and ever and ever and ever, both sides here. We say, here are the first 5 terms. In roster notation, typically we would write it out thusly. We would say 1 is my first term, 4, 7, 10, 13, and then we would put a dot, dot, dot. And this is what we refer to as roster notation. This is roster notation. We're writing it out like a roster. So this would just be a table format. So let's take a look at a few other things really quickly. I need to point them out. But we say a sub n over here. A sub n is our rule. So this is basically, let's get used to calling this our rule. This is our function, okay? And we say what I want to do is find the first 5 terms. So 1, 2, 3, 4, and 5. And we could totally make a table for this. We could say our term and the term value. So 1, 2, 3, 4, and 5. But we say when we plug in 1 here, the thing to notice here is we say our first term would be 3 plus negative 1 to the 1, which is 3 plus negative 1, which is 2. So we say our first term here is 2, 2. And then we say, what if we were to plug in now a sub 2? We say, change this to a 2. Change this to a 2. When you square this negative 1, you get a positive 1 output. We say 3 plus 1 is 4, so we get 4. So we get this right here, okay? And again, we say, well, what if we plugged in a3? We say a3 would be 3 plus negative 1 to the third, which in this case is an odd power, and so we get 3 plus a negative 1, which gives us a 2 again. You could see how this sequence here, it's going to go back and forth forever and ever. So we call this behavior, we're going to give it a name, but we say this sequence oscillates. And if you've never heard of oscillation, basically like a fan, you could have a stand fan, here, it's got one of those things on it, and it goes back and forth essentially, and it blows, out air this way, and it blows out air this way, and it goes back and forth forever and ever. That's oscillation, okay? So we say this sequence oscillates, and of course, we're going to put a dot, dot, dot to indicate that it goes on forever and ever. This last one down here, whenever you have a ratio with 2 different rules, what we'll do is we'll say to find these, what you want to do is you want to evaluate for the top and the bottom differently. So basically, we say write out the first 5 terms. If I plugged in a1, we'd say, well, a1 on the top, we would get negative 1 to the 1, which is negative 1. And we say on the bottom, we get 2 times 1 minus 1. We'd say this is its own rule in and of itself. So we get 2 minus 1, which is 1. So I get negative 1 over 1. So the first term in the sequence is negative 1. If we do this again, however, we say, well, what is a2? I get negative 1 to the 2, which is positive 1, and then 2 times 2 minus 1, which is 3. So I get a third. And you can see how we could keep finding these values here. We say a1, a2, a3 would be just as simple. We say a3. I notice here that in this case I get negative 1 to the third power would be negative 1. And then 2 times 3 minus 1, which is 6 minus 1 is 5. So I get negative 1/5 here, negative 1/5. What I notice is a pattern here. I notice it's going to keep going back positive, negative, positive, negative. So whenever you have a negative 1 to the n, like multiplied by a quantity, you're going to get a sequence that goes back and forth positive and negative. And I also noticed this. I get -1 to the n on top, so it's either going to be -1 or +1 on top, and 2n minus 1 on the bottom. This is like a linear thing. So I notice it keeps going up by 2 every time. If I put this first one over 1, you can see 1 went to 3, went to 5. We're going to get a +1 over 7 this time, and next we get a -1 over 9. And this pattern continues, okay? So that's what sequences are, just a list of numbers in order. We treat them like functions where the domain is just the positive counting numbers. And yeah, we can express them in tables or in roster notation. Cheers.